Hi, welcome back to Vectors. This is Mr. Dale again. As we discussed before, vectors are quantities that have magnitude and direction. We represent them by arrows, and we represent the magnitude by the length of the arrow and the direction, well, by the angle. I want to talk about a little bit about this. So for instance, I'm going to grab this purple vector here, and I can change the magnitude by making it longer or shorter. Direction, obviously by pointing in different ways. Now, how do we measure these things? We need to quantify them, that is, put a number to it. One way we can just measure in centimeters, for instance. Let's say that I got out a ruler, let's pretend, and that I ended up measuring that this was from here to here. Let's say that was 6 centimeters. Now, if the quantity that I'm talking about, let's say displacement, how far am I from where I started? This might be a perfectly legitimate thing. It might mean I've moved 6 centimeters. But often than not, it could be that we want to represent something like a force. We're pulling on something, and we measure force in physics with the unit newtons. So we'd have to have some sort of scaling diagram. For instance, we might say that for every 1 centimeter on this vector equals, let's say, 10 newtons. So what would be the force represented by this purple vector then? I think you probably know. So what I really mean that this is a vector that represents 60 newtons. Now, if we draw things to scale, it's kind of neat because we can actually get a piece of graph paper out and draw these together and figure out how forces add by adding the vectors. It's not too complicated. Now, the other question is, how do we measure the angle? Oftentimes, what we end up doing is referencing everything sort of like back in math class, is we draw sort of an axis and we say that this is 0 degrees. So this blue vector, I might say that, well, this angle appears to be a couple ways you can do it. One way you could say, if I got a protractor or measure this properly, I say that looks to be about minus 40 degrees. For those of you who really loved your geometry class, you might remember, but wait a minute, there's another way we can measure that that's just as legit. And that is if we actually go counterclockwise, sort of the proper way to do it, this would actually be 320 degrees positive, but I'm not going to bother to put the positive sign there. Either way is fine. Another way that sometimes we represent these, I'm getting a little crowded up here, I'm going to move this red guy up here, is that we might say that this vector is pointing south, using our regular map kind of directions. So south would be down, north would be up, east to the right, west to the left. All right, so how do we add vectors? You may have kind of figured this out all by yourself already. Let's see. So let's say that I have this blue vector and a purple vector. I want to add these together. And as I indicated over here, the red vector is the resultant. Well, what would be the resultant? Or basically a vector sum is really all a resultant is. Well, if I stack them, notice that it's head, tail, head to tail, head to tail. If I want to add more, we just keep going head to tail. So I just grab this. And if you're drawing this freshly, I'm going to stick this right under it here and move this over. So there we go. That would be the resultant, or sum of the blue and purple vectors. Another very important thing is that if I take this vector and move it, am I changing it? Not at all. I don't care where I put it. We're allowed to move vectors however we want. We could have just as easily taken the blue and added it this way. We could have said, I don't like this part of the paper. I'm going to do this addition over on this part of the paper. Doesn't matter. We end up with the exact same resultant. We can take advantage of this because we can arrange them however we want to make our lives easy. Now, opposite and parallel vectors. Parallel is probably the easier idea. So let's see, we've got this guy here. Are there any parallel vectors here? No, not really. I'm going to make this guy parallel though by, well, making it parallel. Notice that it doesn't matter what the magnitude is as long as they're in the same direction. That's parallel. How about opposite? So this is going to be a parallel vector, and I'm going to make this one an opposite vector. It's pointing the opposite direction, but you probably kind of knew that anyway. Just wanted you to make sure you were familiar with those terms. All right, let's kind of quantify this now. I'm going to take this vector here. Oh, didn't want to do that. I'm going to move him over. Remember, we can move vectors around anywhere. It does not change the value. That's an important thing to remember. Moving a vector doesn't change it at all. So I want to add these two. And I want to quantify this. What would be the value of this vector? I'm going to go ahead and add some. I'm going to go ahead and add some uh, axes to this. So let's quantify this. Let's put some numbers onto it. Let's see what we've got going here. Well, first, let's see. How do we actually name these vectors? Typically, we actually just give them letter names. Kind of boring, I know, but that's how it goes. So I'm going to go ahead and name this guy A. And to let everyone know it's a vector, we put a little single-headed arrow over it. So that's our vector A. And like imagination, I'm going to call the purple one. Sorry, I didn't mean to do that. I want to make him purple to match. Purple, B. And of course, you can probably see where I'm going with this. This will be vector C. Okay, now they have names. Let's actually give them some numbers now. This is kind of a mathematical thing, so of course we need to deal with numbers. Let's actually put in some axes here. So I'm going to go ahead and just drop an x-axis. And I do want to kind of line up with, there we go, with our grid. And I'm going to go ahead and drop in the x-axis there. And let's see. And I'll just go ahead and call this y and x just like we normally do. And to be proper, we need to indicate that yes, they keep going on and on forever. Okay, so let's see. Let's get back to, let's say, vector b. So right now, we see that this point right here, it starts at point, this would be 0 on the x, and down 2. So it starts at point 0, 2, and it ends right here. And that would be 1, 2, 3 over, and 2 down. So that would be point 3, negative 2. But remember how I said we can move a vector and it doesn't change it? So we've definitely got to figure some way out to represent this. A vector is represented not by these curved parentheses, but by angled brackets. To say, how do I get from the tail to the head? Well, we started at 0, and we end up 3. Well, let's see, how do I figure out how do I get there? Well, it's 3 minus 0. We moved 3 to the right. And what do we do vertically? Oops, actually, I made that wrong. Negative 2. We didn't do anything vertically. So we didn't move it all up or down. So now we would say properly that b, the vector, equals 3, 0. Let's see how that works. If I went ahead and moved the vector over somewhere, and remember I said we can do this wherever we want. So to make life simple, I'm going to go ahead and I'm going to get rid of this guy to begin with. And I'm going to go ahead and move my vector up here. Why did I move it up here? Well, it's on the origin. That makes it really easy. This point is 0, 0. 0, 0. This point over here is 3, 0. Makes it pretty easy. We start from 0. So what is this vector? Well, I think you probably know. It's 3, comma 0. We moved 3 to the right. We didn't move up or down. The same value. Doesn't matter where we move it. So let's see how we add vectors. Let's go ahead and move over, get to a little less crowded area. Again, let's add in some axes. I'm gonna go ahead and move this guy over just a little bit, make sure it's right on there. This guy's a little off too. There we go. And again, let's indicate that these go on forever. Twink. This Y, this are X. Okay. So again, now that I think we've established we can move our vectors however we want, let's make life easy. Let's move this guy over here. Let's move this guy over here. Again, we put them head to tail, head to tail. If I wanted to add in this third guy, I would move it so that we'd move here. And we'll probably play with that a little bit in a sec. So let's see what we've got. We know the resultant. Go ahead and move him over here, start at the bottom, move it over here. So that's our resultant. Again, remember, I can move this guy. It doesn't matter now that I figured this out. Let's see, this vector, we start at 0, 0. We move right 3, not up or down at all. So this vector is 3, 0. Remember, we use these guys. And we're going to add this to this vector, which 1, 2, 3. Not very exciting, exact same values. 3, 0. What's the resultant? Well, we see the red one is we started here and we end up here. What we've done is we've moved to the right 6 and we haven't moved up or down at all. So that's our resultant. You can probably see a shortcut without having to do all this drawing. Basically all we do is we take 3 plus 3, 6. So 3 plus 3, and then we have 0 plus 0, 0. And that's our vector. Pretty easy. So that would say the resultant, the vector, equals 6, 0. Now this works with any sort of vectors. Just add the x's up, add the y's up, and there you have it. Not too bad, right? All right. Well, let's have a look at, make sure you look at all the other readings and the animations that I have assigned for you.